All right, let's jump right in. We're going to go on a little detective story today into the world of physics and look at two of the most mind-bending ideas out there. We're going to unpack the stories we tell about the universe and ask a really simple question. Are they actually true?
So, you've probably heard this one, right? The idea that the vacuum of space isn't truly empty, that it's this chaotic foam, with pairs of virtual particles just popping in and out of existence, borrowing energy from nothing before vanishing in a flash. It's a wild, super compelling image.
And then there's the biggest story of all, the origin story. We've all been fascinated by this idea that our entire cosmos might not have had a specific starting point, that it could have just emerged smoothly from a state of pure space. It's a way to neatly sidestep that whole what came before problem. I mean, these are powerful, really elegant narratives. They totally capture the imagination. But today, we're going to pull back the curtain. We're putting these popular stories under the microscope to see how they hold up when you look at the cold, hard, unforgiving math that physics is built on.
Okay, first up, that bubbling sea of particles, the idea of vacuum fluctuations. Physicist Arnold Neumeier makes a pretty bold claim. He argues that while this is a really powerful story, it's also a deeply misleading myth. And he's actually laid out step by step how this whole story gets built.
So according to Neumeier, here's how the myth gets made. And look, it's not like anyone's trying to mislead you. It's just a series of little leaps that sound good. It starts by giving a name to a piece of math. A line on a diagram becomes a virtual particle. Then you start treating that drawing like it's a photograph of reality. You invent a cool story about borrowing energy to make it all hang together. And then, at the very end, you add this tiny little warning. Don't take this too literally, that, almost everyone forgets. And here's the crucial point. The story is plausible. It feels right. It connects a bunch of different ideas into a story that makes sense. But, and this is the big but, according to Neumeier, it just doesn't have a real basis in the actual formulas of quantum field theory. The math is describing something totally different. It's talking about uncertainties in our measurements, not about some crazy dance party happening in empty space. Look, it's a story that brilliant physicists tell to make their work easier to grasp. But it makes you wonder, right? When do these helpful little stories, these analogies, cross the line and become myths that actually hide the truth instead of revealing it? It's a really fine line to walk.
Okay, let's pivot to our second story. And this one comes from one of the greatest minds in physics, period. It tackles the biggest question of them all. Where did everything, and I mean everything, come from?
For decades, this has been the ultimate question, the one that stumps everybody. The Big Bang Theory tells us the universe expanded from this super hot, super dense state. But that just begs the question, what was there before the bang? What lit the fuse? Well, Stephen Hawking wanted to solve this what came before problem for good. And his solution was, wow. It was so radical, it just changed the whole game. It's called the no-boundary proposal. And it basically says the question itself is flawed. He used this incredible analogy. What's south of the South Pole? Nothing, right? The question doesn't even make sense, because the concept of south ends at the South Pole. Hawking argued that's exactly what time did. There was no before the Big Bang, because that's where time itself began. He and his collaborator, James Hartle, pictured the cosmos shaped kind of like a shuttlecock. It doesn't start with a violent explosion. Instead, it starts as a point of zero size, pure space, which then smoothly and gently widens. Time just sort of emerges as the universe expands. So there's no sharp beginning, no singularity, just the smooth, curved surface at the very bottom. I mean, what a stunningly beautiful and provocative idea. It gives us a self-contained universe, one that doesn't need anything outside of itself to kick things off. It completely reframes how we think about time, suggesting it's not some fundamental background grid, but something that emerges from the universe itself. For decades, this idea was a huge inspiration for physicists. It was really the leading contender for a quantum theory of creation. But here's the thing about physics. Beauty isn't enough. The idea has to work. And recently, a team led by Neil Turek, who actually used to work with Hawking, took a much closer look at the math behind it all. So here's the test. For the no-boundary proposal to be more than just a cool idea, its math has to predict a universe that looks like the one we're living in. Huge, pretty smooth, and mostly flat. Turek's team used some powerful new mathematical tools to see what kind of universe the equations actually spit out when you follow them to the letter. And whoa, the difference between what was hoped for and what they found is just stark. The whole point of the Hartle-Hawking idea was to get a stable universe where little quantum jitters at the start grow into the galaxies we see. But the universe Two Rocks team calculated was the exact opposite. A totally unstable universe where the tiniest fluctuations would spiral out of control, creating a crumpled, chaotic mess. Not our elegant cosmos at all. Yeah, Turk didn't mince words. His conclusion was that if you follow one very specific, rigorous interpretation of the math, the beautiful idea doesn't just stumble. It completely falls apart. It leads to a result that's physically just nonsense. That elegant shuttlecock, it seems, would just shred itself to pieces. Of course, the story isn't over. This is science, after all. It's a debate. Defenders of Hawking's idea argue that Tork's team picked a mathematical path that was pretty much guaranteed to give a weird answer. They say there's a different, equally valid way to do the calculation that leads right back to the smooth, stable universe we live in. So now, the battle is over the fundamental rules of the math itself. So after digging into these two epic stories and the massive debates they've sparked, what's the big takeaway here? What are we supposed to make of all this? Well, it really gets to the heart of what science is all about. The goal isn't just to tell a good story, one that feels nice and makes us think we get it. The stories are the starting point, that spark of intuition. But at the end of the day, they have to survive contact with reality, with cold, hard calculation and experiment. You see, the real story here is the detective work. It's this relentless process of testing and challenging and refining ideas. The debate over the no-boundary proposal and the debunking of the vacuum fluctuation myth, those aren't failures. That's science working exactly like it's supposed to. It's how we weed out the plausible but wrong ideas in the search for a description that isn't just beautiful, but is also true. And that leaves us with one last really provocative thought. We've been trying to fit the universe into these stories about nothingness. But what if the true story of where we came from is something so profoundly different that we don't even have the words or the concepts to describe it yet? Maybe the answer isn't about fixing the stories we have, but about waiting for a completely new one to be written.